Welcome to the MOOCs course Advanced Thermodynamics. The title of this lecture is Vapor Liquid Equilibrium Part 3. It is a continuation of our previous lecture. Last two lectures we have discussed different aspects of vapor liquid equilibrium problems when both phases display ideal behavior, when one of the phase display non-ideal behavior, when both phases display non-ideal behavior. Under such conditions, how to find out the equilibrium composition when two phases are coexisting for a binary as well as multi-component system. Those things we have seen. We have also seen the corresponding phase diagrams and then details associated with these vapor liquid equilibrium problems under both ideal and then non-ideal circumstances. Those things we have already seen in last two lectures. In this lecture we are going to discuss some more details of vapor liquid equilibrium where azeotropes are also formed. What does mean by azeotropes? Azeotropes means, in Greek language, azeotrope means boiling without change. What does it mean? It boils but it does not change, that is composition does not change, that is what it means by. Those details we are going to see in this particular lecture, and then subsequently we will be discussing solubility of liquids in gases and then how to apply the concept of vapor liquid equilibrium for such conditions. Those things also we are going to discuss at the end of this lecture. So, these azeotropes, when deviation from Raoult's law are large enough, then Px, Py curves can exhibit extremes. Extremes in the sense in the Pxy or Txy diagrams that we have seen, there is a kind of a enclosed between Px and then Py curve or Tx and Ty curve, right. That behavior we have seen, a kind of enclosed area we have seen. In that enclosed area we have a kind of a vapor and liquid phases coexisting, and there is one single enclosed areas. But now when there is an azeotrope, what happens? These Px, Py curves or Tx, Ty curves, they show a kind of extreme. Extreme in the sense there may be a kind of a maximum or there may be a kind of minimum is existing, and then because of that one, the envelope, the enclosed area that is forming, which is having which is consisting of both vapor and liquid phases, there will be two enclosed areas or more than one enclosed areas would be there, right. So, why does it occur? Because when the deviation from Raoult's law becomes very large, right. Actually, when there is a deviation from Raoult's law, then obviously the liquid phase is also showing a kind of non-ideality we have seen, but that deviation is very large, then it is possible that there could be a kind of some extremes in Px, Py curves or Tx, Ty curves, right. Because of that extremes, the corresponding pressure, system pressure may be higher or lower than the saturation pressure of both the components of the binary system. So, those things are possible, right. So, if Px curve exhibits a maximum, then Py curve will also exhibit a maximum, and then moreover they exhibit the maximum at the exactly same composition. Let us say Px curve exhibit a kind of a maximum at Xi is equals to 0.6, then Py curve will also exhibit a maximum at the same composition, that is Ya is equals to 0.6, right. And then analogous behavior is observed for minima also. If the Px curve is showing a kind of minima, then Py curve will also show a kind of minima, that is also possible. And this term azeotrope is used to describe this point in the phase diagram where Px, Py curves go through maximum or minimum is described by a term azeotrope. Azeotrope means boiling without changing. Without changing in the sense, when you boil, the obviously composition change, right. That is indirectly more volatile component will go into the vapor phase. So, obviously composition is going to change, right. But at this point that boils, but there will not be any change in the composition. That is what boiling without changing is the meaning in the Greek. About the Greek word azeotrope means boiling without change. So, that is the reason, since in this case also at that particular point the composition does not change, though this mixture is boiling, right. Even by boiling the mixture, the composition is not changing. That is the reason we have used this azeotrope mixture, the term azeotrope, for describing this kind of phenomena. At azeotrope, the mole fraction of each species in the liquid phase equals to that in the vapor phase, that is Xi is equals to Yi at azeotrope. Likewise, their mole fraction must be equal for extremes in temperature curves, that is Tx Py curves also at constant pressure. So, it is not necessary that this. So, that means these extremes, whatever the maxima or minima, they are also possible in Tx Ty curves as well, and under such conditions also at azeotrope xi is equals to yi. We take some examples also. Let us take binary mixture of chloroform and an hexane show large positive deviation from Raoult's law at 318 Kelvin as shown in the picture, right. So, actually this dotted line is for the Raoult's law. If the liquid phase is showing a kind of ideal behavior with reference to Raoult's law, then we have a dotted lines, and this curve is nothing but P y a curve, right. Now, what happens here at this temperature, this chloroform and hexane mixture, it shows a large deviation from the Raoult's law. You can see the deviation is very large, and then this is having the Px curve like this, right, and then it intersects with the Py curve at something around 0.75 or something like that. Okay. And this there is a kind of hysteresis. This is one hysteresis. There is a kind of one enclosed area in this one where both the phases are coexisting, and there is also a small enclosed area other side of the azeotrope also, where also both the phases are coexisting. Okay, right. And then above this Pxa curve, what we have subcooled liquid. Below this Pya curve, we have superheated vapor. Those kind of things are same here also. Other thing that you can see at the azeotrope, whatever the corresponding system pressure is there, that is much higher than the saturation pressure of both these components. You can see from here the saturation pressure of component A is roughly around 57 or something like that, whereas the saturation pressure of component B is around 45 or something like that. The difference is very small. And then system pressure is higher than either of the saturation pressures at the extreme point. Okay. So, these are some characteristics of azeotropes, that around 0.75 it goes through a maximum. Py curve also goes through a maximum at the same composition, that is Ya is equals to 0.75 and touches the Px curve. Now, if you compare this one with the water methanol system or methanol water system that we have previously seen. So, now here this methanol water system, just for comparison I am showing here. So, this we have already seen in our previous lecture. So, here now you can see this is the case when the liquid phase obeys the ideal behavior with reference to the Raoult's law, and then this is if it is having some non-ideality. So, now here this methanol water, it is having some non-ideal behavior like this. Okay. So, that is above this PL curve, and you can see the difference between these two curves, Raoult's law and then Px curve, is very small. Though not very small, it is not very large like in the previous case. In this case, if you see where the azeotrope is forming, now here in this case you can see the difference between these two curves, that RL line, straight line, and then Px curve. You can RL line, the straight line, this RL line, Raoult's law curve, or when the liquid phase obeys the Raoult's law, then whatever the straight line is there, that one, and then Pxa curve when there is a non-ideality. You can see the gap is more compared to the case here in this case where there is no azeotrope formation. Okay. That means when the deviation is low to moderate, when the deviation from Raoult's law is low to moderate, there is no possibility of azeotrope formation. If the deviation from RL is very large, then there is a possibility that there may be azeotrope formation. And then further you can see here saturation pressure of the methanol here in this case is approximately 52 kilopascal or something like that, and then saturation pressure of water, that component B, is around 12 kilopascals. You can see the difference here, almost like 40 kilopascals. That means if the saturation pressures are far away from each other, then also it is not possible or less possible that azeotrope may form. But here in this case where the azeotrope is formed, the difference is hardly 10 to 12 kilopascals. If you compare this PSAT and then PSAT and PBSAT, roughly it is 12 kilopascal only. That is the difference. Whereas here if you see, in the case where there is no azeotrope formation, the difference between these two is approximately 40 kilopascals. So, that means more flatter and horizontal this RL line becomes, the chance of a formation of azeotrope is more, because under such conditions saturation pressure are going to be very close to each other, and then under such conditions unlike interactions may be very much different from the like interactions. That is what we can understand from these two images. Okay. So, but however, both the cases it is showing positive deviation from RL, but here in the case of methanol water system there is no azeotrope formation, because the PXA curve is slightly away from RL line, whereas here in the case of chloroform and N-hexane, the gap between RL line and PXA curve is very large, right. That means in the case of methanol water system, the deviation, positive deviation is there, but it is moderate, whereas in the case of chloroform and N-hexane, deviation is there, but that positive deviation is very large from RL. Okay. These are the few characteristics that you can see. So, what you can understand, when there would be a kind of possibility that azeotrope will form, if the saturation pressures of the two components are close to each other, or the difference between saturation pressure is not very high, if it is very small, then we can say that there is a possibility of azeotrope formation. Okay. So, what does it mean by saturation pressures are close to each other? So, this RL line whatever is there, that slope would be very less, it will not be very steep slope kind of thing. Okay. But azeotrope occurs when deviations are so large that system pressure is pushed above the saturation pressure of lighter component A, as we have seen. Px curve must go through a maximum to return to saturation pressure at pure B, that is PB saturation point. In other words, azeotropes occur when unlike interactions are very different from like interactions. Obviously, they are different from like interaction, then only there is a kind of a deviation from RL, but that difference between this like and unlike interaction is very high, then there is a possibility that azeotrope will form. It can be understood that azeotrope is more likely to occur when saturation pressures of two components are close to each other, that as we have seen in the previous picture. Okay. That is, flatter the straight line representing the ideal solution by RL, the more likely a maximum will result in Py curve. Okay. And then consequently, azeotropes are less common in a binary mixtures with large differences in saturation pressures. If the difference between saturation pressures is large, then it is less likely that the mixture is going to exhibit any kind of azeotrope. If the unlike interactions are stronger than the like interactions, then exactly opposite behavior will occur. What does mean by unlike interactions are stronger? That means negative deviation, right. The previous example of chloroform and hexane, we have seen the positive deviation from RL we have seen. So, but there is a negative deviation, then also it is possible that the azeotrope may form, right. Negative deviation in the sense the unlike interactions are much stronger than the like interactions, then negative deviation from RL will take place, and then if there is a kind of negative deviation under such conditions also there is a possibility that azeotrope may form, again provided the reason is that the saturation pressure for those cases also, if the difference between saturation pressures is not very large, then under the case of negative deviation from ideal behavior also there is a possibility that azeotropes would form, right. Though we have seen that negative deviation from RL is a kind of very rare case, very few examples we find. Okay. In this case of negative deviation from RL, Px, Py curves exhibit minima at exactly same composition, right. So, if it is a positive deviation from RL and there is azeotrope, then there will be a kind of maxima as we have seen in the previous slide in the image. But if there is a negative deviation from RL and there is also possibility of azeotrope, then azeotrope will occur because of exhibiting a kind of minima, that is Px, Py curves exhibiting minima at same composition in the case of negative deviation. We will be seeing an example also. Minima occur if total pressure falls below the saturation pressure of heavier component. In the previous example, where the positive deviation from Raoult's law was there and then there was also azeotrope formation was there. Under such condition, what we have seen, the system pressure goes at the azeotrope higher than the saturation pressure of the both components. But in this case of negative deviation from Raoult's law and there exists azeotrope also, then the system pressure at the azeotrope goes below the or the lower than the saturation pressure of either of the components. Okay. Especially total pressure falls below the saturation pressure of heavier component, that we see pictorially as well here. So, if you take example of acetone and chloroform at 328 Kelvin, then we can see azeotrope may be forming at when Xa is equals to Ya is equals to 0.39 at 73 kilopascals. Pictorially if you see, so now you can see here, yeah. So, now you can see azeotrope is forming at around 0.39, Xa is equals to 0.39 and then system pressure you can see here, system pressure is around 73 kilopascal at the azeotrope. So, the saturation pressure of component B, that is Pb sat, is around 82 kilopascals, whereas the saturation pressure of lighter component A is around 98 kilopascals. Okay. Roughly 98 kilopascal, let us say, right. Here it is 82 kilopascals. Here also the difference is, you can see, 15 to 16 kilopascals only, right. And then system pressure you can see at the azeotrope, it is much lower than either of the saturation pressures. It is around roughly 72 kilopascals or something like that, whereas the saturation pressure of these two components are respectively 97 and then 82 kilopascals respectively for component A and B. Okay. So, here when there is a negative deviation, you can see there is a minima kind of thing is forming in Px and Py curve, and then further you can see obviously there is a deviation from RL line, this is the RL line and then this is your Pxa curve. Now, you can see the difference between this Pxa curve and then RL line is very high. First of all, negative deviation is there and this negative deviation is also very large. As we have seen, if the unlike and like interactions are very much different from each other, then there is a possibility of azeotrope formation. And when the like and unlike interactions are very different from each other, the gap between RL line and Pxa curve is going to be larger, like this we have seen. Okay. And then you can see the enclosed area where both vapor and liquid phases are coexisting. So, this is one area, in this area we have one enclosed area where both the phases are coexisting, and then there is another enclosed area here where again both the both the phases are coexisting and at equilibrium. If there is no azeotrope formation, then we have seen that there is only one enclosed area between Px and Py curve. If there is a azeotrope formation, then it is possible that more than one enclosed area between Px and Py curve representing the coexistence of vapor and liquid phases take place, like this. Okay. One is before the azeotrope point and another one is the after the azeotrope point. Azeotropes showing positive deviation from RL, that is maxima in Px and Py curves, are more common than those exhibiting negative deviations. So, this is a very common observation that negative deviation from ideal behavior represented by RL, very few cases are there, right. So, obviously corresponding azeotropes coexisting along with the negative deviation from RL are also going to be very few compared to the cases of positive deviation coexisting with the azeotropic behavior. Okay. So, azeotrope behavior can also be seen on TXY diagrams also. A mixture in which unlike interactions are weaker than the like interactions will boil more easily than its pure species components. That means what? Unlike interactions are weaker, that means like interactions are stronger. If the like interactions are stronger, that means positive deviation is there. So, if the positive deviation from the RL is there, so then Px, Py curves are showing a kind of maxima if at all there is a kind of azeotrope is there. So, the corresponding Ty curve will be showing a kind of minima, it will be showing a kind of minimum point, right. So, then because Tx, Ty curves are having a kind of minimum point, then it is also called as a kind of minimum boiling mixture. Thus, such system that exhibits a maximum in pressure, that is positive deviation from RL, will exhibit a minimum in temperature like this. So, the same chloroform and hexane system, that Pxy curve will take it positive deviation, okay, and then around at 7.75 we are having a kind of azeotrope point, right. So, if you draw the Txy curve for the same system, but at 1 atmosphere, then you will have this kind of system, where here you can see the azeotrope is formed around at 0.79 or 0.8, and then it is having a kind of a minimum here. In the Pxy diagram, there is a maxima for a positive deviation curve. So, in the Txy curve, there is a minima for the same system showing a positive deviation from the ideal behavior. Okay. As in the case with pressure, a minimum in Ty curve occurs concurrently with minimum in Tx curve at the same composition, and these are known as the minimum boiling azeotropes, because here the mixture boiling point, here we can see what we can understand from here. We can understand at the azeotrope system is boiling at temperature much lower than the boiling point of component B and then boiling point of component A. So, in the minimum boiling azeotropes, system pressure is going to be more than the saturation pressure of either of the components, whereas the system temperature is going to be lower than the boiling point of either of the components A and B. Okay. So, if you wanted to find out whether the system that is exhibiting azeotrope is a minimum boiling azeotrope or maximum boiling azeotrope, then you have to find out the pressure of the system at the azeotropic composition, right. At the azeotropic point, if you find out the system pressure and then if you compare that pressure with the saturation pressure of both the components A and B, if it is more than this saturation pressure, then that is a minimum boiling mixture or minimum boiling azeotrope. If the pressure is less than the saturation pressure of either of the components, then we can say that system is a kind of maximum boiling azeotrope, as we are going to see that example as well. Phase diagram of chloroform and hexane at constant pressure of 1 atmosphere is shown here, and then we can see the azeotrope becomes more likely as the boiling temperature of pure components approach each other, and they differ by only 7 K approximately, 7 Kelvin, right. So, analogously, a binary mixture of acetone and chloroform display a stronger unlike interactions and exhibit a maximum boiling azeotrope at 337 Kelvin with Xa is equals to Ya is equals to 0.39, right. If unlike interactions are stronger, then what we call a negative deviation from RL. If the negative deviation from RL is there, then Px Py curve are going to be below the RL line, right, below the RL line. So, if there is a azeotrope along with this negative deviation, both the behavior are there, then Px Py curve is going to display a kind of a minimum. So, the corresponding behavior in Txy diagram is going to be depicted by the maximum point in Tx Ty curves, and then if in Tx Ty curves there is a maximum, that means the at azeotropic composition system is boiling at a temperature much higher than the boiling temperatures or boiling points of either of the components. Okay. So, that is what we can see here, Txy curve of acetone chloroform, right, and then Pxy curve of the same acetone chloroform system. This is what we have already seen. We have seen that this Pxy curve, there is a azeotrope formation at around 0.39 composition, okay, at around 0.39 of mole fraction for both liquid and vapor phase. So, there is an azeotrope formation, okay. But the corresponding Txy diagram, if you plot at 1 atmosphere, then you can find the azeotrope is forming approximately at the same composition of 0.39, but in the Txy curve we are having a kind of maximum. Whereas the Pxy curve for the same system is showing a kind of minimum, because it is a negative deviation. And now this is the boiling point of component B, and then this is the boiling point of component A, and now as a azeotropic composition at 0.39, the system temperature is much higher than this either two boiling points of two components A and B respectively, right. So, the system is boiling at higher temperature than the boiling point of either of the two components at the azeotropic composition. So, that is the reason these kind of azeotropes are known as the maximum boiling azeotropes. And then here also you can see the difference between boiling point of these two components is approximately 7 Kelvin, as we have seen previously, it is the same system. Okay. So, this is what we can understand. So, that means if there is azeotrope, then if the Pxy curve is showing a kind of minimum, then Txy curve is going to show a kind of a maximum, right. And then if there is azeotrope and then system Pxy diagram is showing a kind of maximum, then corresponding Txy curve is going to show a kind of a minimum. Okay. Opposite trend we see. So, that is to recapitulate, let us say if you have the azeotropes, then Pxy curve, if there is a kind of maximum is existing. So, there will be a kind of a minimum in corresponding Txy phase diagram, and then such mixtures are known as the not mixtures, the mixture at that azeotropic point is known as the minimum boiling azeotropes. And then if Pxy curve is having a kind of minimum in its Pxy phase diagram, then corresponding Txy curve is going to have a kind of or display a kind of a maximum, then that means the azeotropic mixture is boiling at maximum boiling point, or known as the maximum boiling azeotropes. So, this is about a few characteristics about the azeotrope. So, what we understand, obviously azeotropes are undesirable, because we know when this yi and then xi, the difference between yi and xi is small, then the separation is going to be difficult, that we already understand. Now, in the case of azeotrope, what happens, this yi is becoming equal to the xi, that means separation is not possible, separation is not at all possible. While azeotropes are undesirable from a processing point of view, we can take advantage of the phenomena in obtaining parameters for model of GE. Let us say 2 suffix parameter A is there or 3 suffix parameters A, B are there. So, if you know there is azeotrope formation for a given system, so then that information may be used to find out these parameters. Because vapor and liquid compositions are equal at azeotrope, at equilibrium for component A we can write FAV is equals to FAL. That means, if the system is, let us say, is having a kind of non-ideality only in the liquid side, where vapor side is a kind of ideal one, then we can write it as YAP is equals to XA gamma A PSat. And now at azeotrope, this YA and XA both are equal to each other, then we can write P is equals to gamma A PSat or gamma A is equals to P by Psat. That means, at azeotropic composition, if you wanted to know the activity coefficient of a given component, you need to know only the system total pressure and then saturation pressure of that particular component, because the ratio of the system total pressure to saturation pressure of that component gives the activity coefficient of that component at azeotropic composition, right. Now, similarly for a component B also, if you write, you get gamma B is equals to P by Pb sat. That means, gamma A by gamma B is nothing but Pb sat by Pa sat. This is one additional information you get. This is another additional information you get. And now, using these equations, you can find out what is this constant associated with GE model, etc. Those things you can find out. So, this is the advantage, mathematical advantage only, but operational wise azeotrope is always going to be undesirable. Now, this is all about the characteristics of azeotropes, but can we prove it thermodynamically? That is what we are going to see now. Okay. Thermodynamic proof of Xi is equals to Yi at azeotrope. So, we start with equal chemical potential, that is mu I alpha is equals to mu I beta. If you have alpha and beta phase, then for ith component this is what we can write. Now, what you do? You divide this equation by temperature T, that is mu I alpha by T is equals to mu I beta by T. Now, what you do? You take this temperature, pressure and then composition as a kind of independent variables and then try to obtain differentiation of this particular equation. Then what you have? Dou by dou t of mu I alpha by t dt plus dou by dou p of mu I alpha by t dp plus dou by dou xi alpha of mu I alpha by t dxi alpha. That should be equals to dou by dou t of mu I beta by t dt plus dou by dou p of mu I beta by t dp plus dou by dou xi beta of mu I beta by t dxi beta. This is what you get. Now, in the next step, what you do? This t you can take it out of partial differentiation, because it is at constant Txm. Same is here also. This t you can also take out of the partial differentiation, because it is at constant T and P. Likewise, same is true for the beta phase also. When you do this thing, so here 1 by T dou mu I alpha by dou p you will get, and then here 1 by T dou mu I alpha by dou xi alpha you will get. Same is true in the right hand side also. Now, at the beginning of this particular course, when we are discussing about the chemical potential, what we understood? We understood that dou mu I by dou p is nothing but V I bar, and also we understand that dou mu I by dou t is nothing but minus H I bar by t. That is what we understand. So, here you will get minus H I bar alpha by t square, and then for this part you will get V I bar alpha by T is as it is, this will remain same, and then same is true for the beta phase terms also. That if you do, you will get this equation minus H I bar alpha by T square dt plus V I bar alpha by T dP plus 1 by T dou mu I alpha by dou x I alpha dx I alpha, and then same is true for the beta phase in the right hand side. Then here in this equation what we have, this H I bar is nothing but partial molar enthalpy of component I, and then V I bar is nothing but partial molar volume of I. Now, let us write this equation by taking alpha phase as vapor phase and beta phase as liquid phase, because this is we are trying to this in mathematical thermodynamic simplification we are trying to find out thermodynamically can we prove that xi is equals to yi or not, that is vapor and liquid phases are there. So, then alpha phase we are taking as vapor phase and beta phase we are taking as a liquid phase. Then same equation, exactly the same thing, that alpha is replaced by V and then beta is replaced by L, indicating vapor and liquid phases respectively, right. Now, this equation we write for binary mixture simplicity, just for simplicity we write it for the binary mixture. So, this is a generalized equation for any component I in the mixture, right. If there are m number of components, there are m number of such relations would be there. So, now for simplicity we take binary mixture A B. So, two relations would be there. So, for component A this relation, for component B we have this relation. Now, what we do, whatever the dou mu I by dou y or dou mu I by dou x terms are there, those terms will be keeping one side and then remaining terms will be taking to the other side for both of these equations. When we do, then we get this equation number 3 and then equation number 4 like this. But we have a Gibbs-Duhem equation for liquid phase. If you write, this is what you can have, xa d mu al plus xb d mu bl is equals to 0, that I have written with respect to partial differentiation xa here for simplicity. Same is true for the vapor phase also. If you write Gibbs-Duhem equation, then you have this equation, that is simply sigma ni d mu I is equals to 0 or sigma xi d mu I is equals to 0, either way we can write. This we are writing for both vapor and liquid phase. So, then we have this equation. Now, what I do, this equation number 3 I will multiply by ya both sides, and then equation number 4 what I do, I will multiply both sides by 1 minus ya. Like this, and then add them together, and then if you add them together, so what you have here, ya dou mu a v by dou ya, you are having one term, and then another term you will be having 1 minus ya dou mu b v by dou ya, this term you are having. So, if you take the minus common, so then this term plus this term, when you do, what will happen, that is nothing but 0 according to equation number 6, and then remaining terms would be there. So, these two terms ya multiplied by this term plus 1 minus ya multiplied by this term is equals to ya multiplied by this term plus 1 minus ya multiplied by this term, then plus ya multiplied by this term plus 1 minus ya multiplied by this term, that is what you have. So, then finally, when you strike off these two terms using equation number 6, these first terms would be 0, and then remaining 6 terms, if you rewrite after making use of this expression also, and then doing some kind of algebraic simplifications, then you will have this term. Final equation you will get this one. This one plus this term is also be there. So, that is by multiplying this equation number 3 by y a and then multiplying equation number 4 by 1 minus y a either side and then adding them together, what we can understand, we will be having a term y a dou mu a v by dou y a plus 1 minus y a dou mu b by dou y a will be having, that is nothing but 0 according to Gibbs-de Haas equation for the vapor phase. And then similarly, remaining terms also, if you apply the Gibbs-de Haas equation term for the liquid phase and then simplify, then if you do some kind of algebraic simplification, then you get this equation. So, now this dxa if I take to the right hand side, then what we will have? I will be having y a minus x a by 1 minus x a dou mu a l by dou x a is equals to this entire term multiplied by dou t by dou x a at constant p minus this entire term multiplied by dou p by dou x a at constant t. Now, from the azeotropic discussions, that what we understand, there is a kind of maxima in Txa curve and then Pxa curve also, right. So, that means if the maxima is occurring at a certain composition, then at that composition dou t by dou x is 0, dou t by dou y is 0, if it is Txy curve. And then similarly, in the case of Pxy curve also there is a maxima, then at that maxima composition, at that particular composition where the maxima is occurring for Px and Py curve, then at that point we can write dou p by dou xa is equals to 0 as well as dou p by dou y is equals to 0. That means at the azeotrope dou t by dou x is 0, dou p by dou x is also 0. That means altogether right hand side both the terms are 0. So, that means left hand side is equals to 0, then what we can understand, if this left hand side is equals to 0, from here what we can understand? We can understand y a is equals to x a. So, even thermodynamically it is proved that azeotrope is possible, okay. That is what it means by. So, under extreme conditions dou t by dou x a is equals to 0 or dou p by dou x a is equals to 0. These extreme conditions means that when system goes through an extreme, here maxima in temperature with respect to x a at constant p or an extreme in pressure with respect to x a at constant t, then mole fractions in each phase must be equal, that is x a is equals to y a, as we have seen proved in the previous slide. So, that is about the thermodynamic proof of existence of azeotropic, or at the azeotropic point the composition of a component in either of the phase is equal, okay, if at all there is azeotrope is forming, or at the azeotropic point the composition of component I in the vapor phase is equals to the composition of component I in the liquid phase. That is what we have already proved, okay. Now, having seen some characteristics of this azeotropic behavior and then having seen the proof, thermodynamic proof of this equal composition at azeotropic point, now what we do? We go to a few example problem to make sure how we can use this azeotropic conditions. So, here at 50 degree centigrade, a binary mixture of 1,4-dioxane and water exhibits an azeotrope at Xa is equals to 0.554 and a pressure of 0.223 bar, and then use this datum to estimate the value of 2 suffix Morgell's parameter A. So, 2 suffix Morgell's equation we know ln gamma A is equals to A by RT x b square, that means A is equals to RT ln gamma A by x b square. Now, from steam tables at 50 degree centigrade we know for water the saturation pressure is Pb sat is equals to 0.124 bar, and then similarly if you obtain the Antoine constant for this 1,4-dioxane, and then apply the Antoine equation to find out the saturation pressure of this component A, then you can find out this PSat as 0.156 bar at 50 degree centigrade. This I am not doing, just take it, because such kind of things we have already done several problems how to find out the saturation pressures. And then at azeotrope, what we know that gamma A is nothing but P by P sat, isn't it? Because we have this YAP is equals to XA P A sat, and then there is a gamma A, if at all non-ideality is there in the liquid phase only. Then at azeotrope this XA, YA are equal, that means gamma A is equals to P by P A sat. So, that we have seen. So, that we apply, then you get gamma A is equals to 1.43. Once gamma A is known, so this A is equals to RT ln gamma A by XB square you can use to find out A value, right. XA is given as 0.554, so XB is nothing but 0.446. So, that you can substitute. So, here and then gamma A you find just now as 1.43, then you get A is equals to 4826 joule per mole. Then you get A is equals to 4826 joule per mole. Then similarly for component B also, YBP is equals to XB PB sat gamma B, XB YB are equal to each other at azeotropic point. So, gamma B is nothing but P by PB sat, and then when you apply this one you get gamma B is equals to 1.81, and then from this gamma B information ln gamma B is nothing but A by RT XA square. That means A is equals to RT ln gamma B by XA square for 2 suffix Morgul's equation. Ln gamma B you substitute whatever 1.81 and XA is nothing but 0.554. When you do it you get 5174 joule per mole as this parameter A. Now, you can see by either of these two approaches we are getting different values of A. One is 4826, another one is 5174. Though the difference is not much, so that can be avoided, any of this value can be taken, or better you take the average value. Average value comes out to be 5000 joule per mole or 5 kilojoules per mole is the value of this 2 suffix parameter or 2 suffix Morgul's parameter A. Okay. Now, we take another example. A mixture of methanol and ethyl acetate exhibits an azeotrope at 55 degree centigrade. PA-sat is given as 68.8 kilopascal, PB-sat is given as 46.5 kilopascals. The liquid phase non-ideality can be obtained by 2 suffix Morgul's equation with parameter A is equals to 2900 joule per mole. What is the pressure and composition of the azeotrope? Right. Now, the question is the other way. Previous problem is that azeotropic composition and then pressure is given. So, we were to find out the parameter A. Now, the parameter A and then saturation pressures are given, temperature is given. So, we have to find out the pressure and then azeotropic composition. Azeotropic composition and then corresponding pressure we have to find out, and then we have to check whether is it a minimum or maximum boiling azeotrope. Assume vapor phase is ideal. So, non-ideality is there only in the liquid phase, right. If you wanted to know whether it is a minimum boiling azeotrope or maximum boiling azeotrope, you have to find out the pressure at the azeotropic composition. If that pressure is higher than the saturation pressures of both the components, then we can say it is a minimum boiling azeotrope. Otherwise, it is a maximum boiling azeotrope. Okay. So, first we have to find out pressure. So, for component A and B, if you write equilibrium relation, then YAP is equals to XA gamma A PA sat, and then YBP is equals to XB gamma B PB sat. If you apply this azeotrope, that is YA is equals to XA and then YB is equals to XB at azeotrope, then we have P is equals to gamma A PA sat and then P is equals to gamma B PB sat. And then 2 suffix Morgul's equation, we know that ln gamma A is equals to A by RT x b square and then ln gamma b is equals to a by RT x square. This we have already derived, right. Then this gamma a in place of gamma a and then in place of gamma b, we can have this information whatever exponential of a by RT 1 minus x b square and then exponential of a by RT x square respectively for gamma a and gamma b. Because from this relation what we are having? We are having gamma a P A sat is equals to gamma b P B sat. Now, P A sat, P B sat are given, A is also given, only thing unknown is X A here. Temperature is also given 55 degree centigrade. So, you substitute all of them here and then solve this equation for X A, then you will find it out as 0.68. So, azeotropic composition is nothing but X A is equals to 0.68 and then Y A is equals to 0.68. But we have to find out the pressure also. P is nothing but gamma A P A sat or gamma B P B sat. So, you have to find out what is gamma A, gamma B if you wanted to find out the pressure. Since X A, X B are already known, already calculated. So, gamma B can be or gamma A can be calculated easily, right. Gamma A is equals to exponential of A by RT x b square. So, this is A given, x b we found it as 0.32, this is R, this is T. So, gamma A you will get 1.11. Then P is nothing but gamma A P A sat at azeotropic composition. At azeotropic composition P is nothing but gamma A P A sat. When you do it, you will find it out as 76.4 kilopascals. Now, what is P A sat? What is P B sat? You have to compare this P with these two values, then only you can say whether it is maximum boiling or minimum boiling mixture. So, P A sat is 68.8, P B sat is 46.5, right, 68.8, 46.5. So, the system pressure at the azeotropic composition is higher than the either of the saturation pressure values for component A and B respectively. So, that means it is a minimum boiling azeotrope, it is a minimum boiling azeotrope. Now, we see a few details about solubility of gases in liquids using the same principles of vapor liquid equilibrium, that is viscosity of component I in gaseous phase is equals to viscosity of component I in the liquid phase. That principle we use and then we try to establish some relations here. But before going into details, what we should understand, whatever the analysis that we have done, vapor liquid equilibrium analysis for ideal, non-ideal system as well, even for the azeotropic calculations also, the reference state mostly we have taken either Lewis-Randall reference state or Raoult's law kind of thing, those things only we have taken. But we already know that Henry's law is also a kind of reference state for defining non-ideality or ideality of a liquid phase. When we take Henry's law as a kind of reference state, if the unlike interactions are dominating and they are different from the like interactions, then we should have a kind of information about Henry's law constant. Under such conditions, we can use this Henry's law as a kind of a reference state. Or when xi tends to 0, then that means we can say that component I is very sparingly soluble in the solvent. So, under such conditions also we can use this Henry's law as a kind of reference state. And then solubility of gases in liquid is in general falls on in that category only. These gases soluble in the liquid, but they are soluble in very small amount. So, under such conditions we can use the same vapor liquid equilibrium principles, that FIV is equals to FIL, but here the reference state has to be Henry's law reference state, because these gaseous components are very sparingly soluble in the liquids in general. For those cases we are going to see now here. Solubility of gases in liquids is another important class of VLE problem. For examples, gases dissolved in seawater are crucial to the biology of marine species. Also, fish require dissolved oxygen and give off CO2, while algae performing photosynthesis consume CO2 and then emit oxygen, right. Suppose if one want to calculate the amount of oxygen dissolved in water for a system at 1 bar and 25 degrees centigrade, then how should it be done? Is it possible or not? But pure O2 has a critical temperature of 154.6 Kelvin. So, obviously at 25 degrees centigrade pure O2 cannot be liquid, because for pure O2 Tc or critical temperature is nothing but 154.6 Kelvin. So, obviously it will exist as a supercritical fluid at temperature of the system, that is whatever 25 degrees centigrade we have taken. Okay. So, thus it is problematic to calculate its pure species fugacity in liquid phase and apply a Lewis-Randall reference state. So, that is not possible. So, alternatively what we can use? We can use Henry's law to express the liquid fugacity for oxygen O2. In general, it is common to use a Henry's law reference state for a species when system temperature is well above that species critical temperature, as we have seen the example of oxygen. In such case, an alternative approach is given by extrapolating for a hypothetical saturation pressure using Clausius-Clapeyron equation and then using LR reference state, that is also possible. But in present system of dissolved oxygen in water, dissolved gas is referred as a solute while H2O is termed as the solvent. Since Henry's law is indicative of unlike interactions, AB interactions, Henry's constants depends not only on the identity of solute, but also on the identity of the solvent, because solute, the same solute, if you dissolve in different solvent, the solubility is going to be different. So, obviously the Henry's law constant is going to be different for the same solute in different solvent. For example, if you take Henry's constant for N2 in C6H6 is roughly 3 times less than that in CS2. Solute is same, but solvent is different in 2 cases. That is because why it happens? Polarizability of C6H6 is greater than that of CS2, and thus London attractions or London interactions are stronger in the case of C6H6. So, since the stronger unlike attractive interaction leads to lower the tendency to escape and therefore, a lower Henry's constant for N2 in C6H6 one can find, that is the reason. So, this is one of the examples, and then other examples may also be there, and then similar analysis one can find out why solubility of one particular solute in different solvents are going to be different. So, now in order to solve equilibrium composition of the solute using Henry's law, we can apply this principle FIV is equals to FIL, and then applying Henry's law constant, when we have both phases non-ideality, generalized one we are writing. So, then for the vapor phase or the gaseous phase, Yi phi p is equals to for the liquid phase whatever the xi gamma I Fi naught. Now, till now what we have taken Fi naught with reference to Lewis-Randall rule, Fi naught we have taken as F pure I, and then for pure component F pure I is nothing but Pi sat or saturation pressure of that component I, if the pressure is low to moderate, that is what we have taken. But now we are taking Henry's law as a kind of reference here. So, Fi naught has to be Hi, that is the solubility of component I in the solvent, and then whatever the activity coefficient is there, that gamma I we are representing gamma I H, because whatever the activity coefficients those we have derived, there also we have taken either the Lewis-Randall reference rule or the Raoult's law as a kind of reference, and then we got this activity coefficient, etc. Indirectly whatever the GE expression, GE tends to 0 when x1 tends to 0 or x2 tends to 0, that is what we have taken, that is nothing but with reference to the Raoult's law. Okay. So, but here we are taking this activity coefficient also one has to calculate by taking that xi tends to 0, then Fi naught is equals to Hi that we are taking. So, the corresponding activity coefficient whatever is there, that is we are representing as gamma I H. How to calculate gamma I H, that is what we are going to see anyway. So, now case 1, first case we take dissolved gas solute A in the liquid solvent B, and then when both the phases are obeying ideal behavior, and then that is assume gas mixture is obeying ideal gas law, and in the limit of sparring solubility of gas A in the liquid consists of almost all B. Thus, solute species A acts ideally in Henry's law limit, that is behavior is dominated by the AB interactions, whereas the for B it is same Lewis-Randall reference law is applicable, but the solvent species B is almost all pure B and is ideal in the LR limit, that is all BB interactions are there for species B. So, with respect to component A, which is sparingly soluble in the solvent, right, Xa is tends to 0 or very small. So, for that component whatever Fi naught is there, that can be taken as Ha, whereas with respect to B, this B is almost pure. So, then for this case Fi naught should be taken as F pure I. So, that is nothing but Pi sat that we can take. So, that is the difference here compared to the previous one, right. So, then what we have for component A, YAP is equals to XA gamma A and then Fi naught. Fi naught is Ha here, and then gamma A we are taking liquid phase is ideal. So, gamma A H will also be 1, and then for component B here YBP for the vapor phase is okay, but for the liquid phase XB gamma B and then Fi naught. Gamma B is also 1 because we are taking ideal liquid phase, and then Fi naught with respect to B what we are seeing almost pure B is there. So, Fi naught should be F pure I. So, that is F pure B, and then that is nothing but PB sat, and that is nothing but PB sat at low to moderate pressures. When it is low to moderate pressures, then only you can say it is a ideal behavior for the vapor phase or gas phase, right. So, this is the difference now here. In the previous case when we take for both the components, if you take the Lewis-Randall rule as a reference state, then here we previously we got PA sat, but now it is not true here in this case. Here in this case of sparingly soluble A, it is not true, whereas for the component B it is same as in the previous case of vapor liquid equilibrium whatever we have done. So, now if you add them together, YAP plus YBP is nothing but P, that is nothing but XA HA plus XB PB sat. So, now this if you substitute in equation 3 and 4, then you can find it out. YA is equals to XA HA divided by XA HA plus XB PB sat, and then YB is nothing but XB PB sat divided by XA HA plus XB PB sat, right. So, in general these whatever this equation number 6 is there or this equation number 3 whatever these two are there, they are valid only when Xa is up to 0.03 only. Sometimes it is well beyond this limit also. If it is more than 0.05, in general you cannot take as a kind of Henry's law as a reference. It is true only when Xa tends to 0, very small. So, now we take the case 2, if there is enough of a lighter component in the liquid, so that there is a non-ideality in the liquid phase, but the vapor phase is still ideal, then both AA and AB interactions become important in describing fugacity of liquid phase, and thus one must account for non-ideal behavior in the liquid phase. Then we have for component A YAP vapor phase is still ideal, and then liquid phase Xa gamma H HA we have, okay. and then this component B Yb P and then Xb this gamma B and then Pb sat, because Xb tends to 1. So, then Fb naught is nothing but F pure B is nothing but Pb sat. Whereas, such reference state we cannot use, because here in the case of Xa tends to 0. So, then Fa naught is nothing but Ha, and then corresponding activity coefficient is nothing but gamma AH. Okay. This is the difference. Whatever the difference compared to the previous 2 lectures, that equation that we have used, that is coming in this component A, because component A is only sparingly soluble in component B. So, when you add them together, what we have? YAP plus YBP is equals to P is equals to XA gamma AH HA plus XB gamma B PB sat, right. Then YA you will get XA HA by this one, and then YB is nothing but XB PB sat by this one P, whatever the total P. Fine. Now, similarly, if you take high pressures, but liquid is ideal. High pressures, that means vapor is non-ideal, but liquid we are taking as a kind of ideal behavior. Then for component YA FAP is equals to XA HA, and then component B YA FBP is equals to XB FBL, right. Now, here what happens at high pressures, this whatever the HA in general available at 1 bar pressure, but the pressure is higher one, then we have to make a kind of correction to this Henry's constant. That correction is nothing but exponential of integral Vi bar infinity by RT dP. Now, here I is nothing but A, and then integration from 1 bar to the pressure at which you wanted to update this Henry's constant or correct this Henry's constant. So, that is what you should have, and then Fb is nothing but Pb sat Pb sat exponential of Vbl by RT dP Pb sat to P. This is also we have seen for pure component A, because B component is almost pure component now here, okay. And then pressure is high, right. So, here the pressure is high, that is the reason we are writing this one. Pressure is high, that is the reason we have to write this one. If the pressure is low to moderate, then we can write this FBL or is simply nothing but PB sat we can write, if the pressure is low to moderate. But the pressure is not low to moderate, because when the pressure is low to moderate, then what happens, this PB sat is close to 1, and then this exponential term Poynting correction what we have seen, it is close to 1. If the pressure or delta P is less than 10 bar, that is what we have seen for typical cases. Then under such conditions FBL is obviously become PB sat, but in this case the pressure is high. So, we cannot say this exponential term Poynting correction is close to 1, it is having certain value, and then we cannot say that PB sat is equals to 1, it will also have some kind of value. So, that is the reason this is what we are having, right. So, that means YA FAP is equals to XA HA at 1 bar exponential of Va bar infinity by RT dP integration from 1 bar to P, and then Yb FBP is equals to XB PB sat exponential of Vbl by RT dP, and then integration from PB sat to P, right. So, these are the equations. Now, in the last case non-ideal liquid and then pressure is also very high, then both phases, liquid is anyway non-ideal we are saying, if the pressure is also very high, then vapor is also non-ideal. Then under such conditions we have this the same expression whatever we are having, this one, that will be in the right hand side multiplied with this activity coefficient. Only difference from case 3 to case 3 is the case 4 is different from case 3 by non-ideality in the liquid phase also. That non-ideality in the liquid phase for component A is brought through that gamma AH. So, that is added here, and then for component B non-ideality is added through this gamma B here. That is it. These are the corresponding equations if you wanted to find out solubility of gases in liquids, and then depending on the pressure, low pressure, high pressure, or the ideal vapor or ideal liquid, or one of them is ideal, another one is non-ideal, or both of them are non-ideal, then accordingly out of these 4 cases which case is matching one has to find out and then apply to find out the problems or to solve the problems associated with the solubility of gases in liquids. So, with this we completed almost all required information about vapor liquid equilibrium. The references for this lecture are provided here, but the entire lecture is prepared from this reference book by Koretsky. Thank you.